Hello, everyone. Thanks for your patience. Sorry for the delay in this video, and sorry we couldn't meet today. Today is the 21st. This video will walk you through the first lesson, or lesson 9A, um, which covers the topic from Thursday, exponential functions. Today we're going to talk about exponential growth versus decay, because last week we graphed both types of functions. So please make sure you have Desmos open, desmos.com/practice, and be prepared to pause this video whenever you need to write notes or change your answers if you've already completed the packet. Okay? Excuse me. So for the do now, which of the following will have a greater value? And how can we tell without using a calculator? 1.3 to the power of 10 or 0.5 to the power of 10? 1.3 to the power of 10 should be bigger when written in standard form, so circle it, because 1.3 to the power of 10 is 1.3 multiplied by itself 10 times. 0.5 to the power of 10 would be 0.5 multiplied by itself 10 times. Sorry, let me reshare that screen. Okay, so we can just write that down. We know that exponents represent multiplication or repeated multiplication, multiplying by the same number over and over again. We can also think of it as 1.3 is 1 plus 0.3 multiplied by itself 10 times, whereas 0.5 is 1 minus 0.5 multiplied by itself 10 times. So, of course, addition sentences or expressions that are being multiplied 10 times will be bigger than subtraction expressions that are multiplied by themselves 10 times. And we're actually going to use this bottom way to focus on our lesson today. So please make sure you have everything written on the do now. Again, pause it if you need to, and then flip your page. All right, let's flip. Here is a blast from the past. We're going to use these scenarios to model some exponential functions later. So let's take a look at this first blast from the past. The price of a jacket is $450. A discount of 15% is applied. What is the price to be paid assuming there is no tax? So you may have remembered that from middle school that when you work with percents in operations or word problems, you have to convert them to decimals. You do that by multiplying them by, by dividing them by 100%. By 100. Let me say that again. Take your percent and divide it by 100 to convert it to a decimal. So the first thing to do right there in the word problem is underline your 15% or box it and divide it by 100, 0.15. That's the discount amount. Discount means the amount that you're not going to pay. So we can multiply 450 by 0.15 to find out the discount amount, $67.50. You can just type that right into Desmos. That's not what the question's asking for, though. The question's asking what is the price to be paid. So we take the original amount and subtract the discount, $382.50. The second one, if a person's gross income is $87,000 and that is taxed at 4.7, what is the resulting net income? So if you're 4.7%, you need to divide that by 100. There's no value in the tens place of this percent. So our decimal will actually have a zero to start, 0.047. It's also important to know that gross pay is the amount you get before being taxed, and then your net pay is what you get after tax. We pay tax to our government and in our weekly like salaries um so that it's paid. We actually earn less than what our gross pay is states. And so we take 87,000 and multiply it by that percent, 0.047. You get the amount that you pay in tax. And then subtract the tax amount, 87,000 minus 4,089 to get how much net pay you have. And reading the note at the bottom, why did we do this? Well, to find the percent of a number, you must multiply the percent by the given value. So that's why we're going to use them with exponential functions, because we learned already that exponents represent multiplication. Before we flip over, I'm going to write in red. There was actually another way to do this without having to do two operations. In number one, if we know that there's a 15% discount, before multiplying the 15% discount, we could have multiplied a different percent. 100% is the original price or original amount. That's the most something is. 100% represents an original amount. If I took away 15, I would get 85% paid. We take away 15 for that discount. And if I multiplied 450 by 0.85, check on Desmos, you'll see we get 382.5 or 0.50. That's the amount paid. So instead of multiplying by 0.15, you could have multiplied by 0.85 to get your answer in maybe less steps. Same thing on the bottom here, number 2. Instead of multiplying by 0.47, we could have multiplied 87,000 by whatever 100% minus 4.7% is, or whatever 1 minus 0.047 is. So if we check 1 minus 0.047 is 1 minus 0.047 is 0.953. Or 82,911. So you could have gotten again in one step. All right, let's keep going. Number 3, the price of an apple increases by 1% each year. How much would it cost in 3 years if an apple is $2? Build a geometric sequence to help you determine your answer. And what you may think is that if it says 3 years, you need 3 slots in your sequence, but the first slot actually represents the cost right now. So we need 4 slots to get to the 3rd year, or 3 years after right now. We know right now it costs $2. It's increasing by 1% each year, underline that. And that's another way we've learned how to work with percents in middle school. Percent increase. If it's increasing by 1% each year, we shouldn't multiply by 1%. We should actually be multiplying by 1% more than $2. So how do we represent that more than? Well, $2 is the original amount, and original is represented by 100%. So we can actually say that increases by 100%, by 1%, is 100% plus 1%. Every year we're going to have 101% of last year. We're going to have the original 100 plus 1 more percent. So we take 101. Let's do it on the bottom. We divide it by 100 to turn it into a decimal because we can't put percents into our word problems. That's 1.01. And we know 1.01 is really just 1 plus 0.01, or the 100% original plus a 1% increase. And so that's what we're going to multiply by every year. So we take in our arrow from now to year one, we take $2 and we multiply, put the dot, multiply by 1.01. And that's 2.02. So next year it'll cost $2.02. Then we multiply by 1.01 again, and it's going to cost 2.02 times 1.01, 2.0402, or $2.04 when we round it. Multiply that value by 1.01, 2.060602, $2.06 by year three. When we round, not by year three, sorry, 3 years from now. How could you have solved this problem using a formula we learned? Last week we learned the exponential, let's write it exp, the exponential function or the exponential formula. F of x equals, or y equals a times b to the power of x, where a is the initial value. Let's write it down. And b is the common factor. The initial value here for the apple was $2. It costs $2 right now. The common factor in our sequence is what we were multiplying by over and over again. And every year we're multiplying by 1.01. It's increasing by 1%. And this makes sense because if we're multiplying by 1.01 every year, then 1.01 is our base raised to the power of x, where x is whatever year we're looking for. And don't forget 2 in front of it, the initial value, equals y. So that's the formula. I'm sorry, if you wrote that, erase it. Something else we should note is that x equals 3, because we're looking for 3 years from now. 3 years. And so now let's write the equation. Y equals a times b to the power of x. Y equals 2 times 1.01 to the power of 3. Type that in left to right on Desmos, and you get 2.060602, or $2.06 in 3 years. Okay. The price of a computer decreases by 3.2% every 4 years. I'm going to do it in a different color. Decreases by 3.2% every 4 years. So instead of every year, every 4 years. How much would it cost in 20 years, underline it, if the computer is currently valued at $3,700? Use the exponential formula to determine your answer. The first thing to do here is note that it's not decreasing every year, it's decreasing every 4 years. So if I'm looking at 20 years, it's not 20 years of decreasing, it's 20 divided by 4. It's only 5 years of decreasing. It's only 5 times where I multiply. So my exponent is really 5. X equals 5 years. When we're using the formula y equals a times b to the power of x, x, the exponent, represents the amount of time periods. So here a is $3,700. That's the starting amount or the initial value. B is how much it's decreasing by. So it's 100% to start minus 3.2%. Another way to write it is 96.8%. 96.8% divided by 100 is 0.968. That's our b-value. We start with 100%. That's the 100% price is $3,700. That's what it's currently valued at. That's 100% of its price. Next year, it's going to be 96.8% of its worth. It went down by 3.2%. So every year it's going down by 0.968. Y equals 3,700 times 0.968 to the power of x, where x is 5. 3,144.69. Okay, so it decreased by 3.2%, meaning our b value, what we multiply by every year or every 4 years, is 96.8% of the price. In the last example, it increased by 100%. So we go up 100, we're multiplying by 101% every year, or 1.01. Our b value was bigger than 1. Now our b value is less than 1. Let's go to the next page. It says yesterday, but that was last week. Last week, we learned how to graph exponential functions given in the form y equals a times b to the power of x, where a is the initial value or y-intercept. B is the common factor. These values can also be found within word problems and used to write equations that model exponential situations. So we can look for A and B within a word problem and write the equation by plugging in A and B into this standard form. So when percents are being used, we are going to use B a little differently, like we saw on the last page. When percents are being multiplied to a starting value over X amount of time, there's a special way to apply the exponential formula. You should be prepared to write it on your reference sheet on the day of the Regents. Here it is. This is not provided on the Regents, so you should memorize it. Y equals A, parentheses 1 plus or minus R to the power of X. A is the initial value, as always, as for any exponential formula. R is the percentage by which the original amount is increasing or decreasing. Let's box that. R is the percentage. B is the common factor. B is the number we multiply by. But here, B is split up as to 1 plus or minus R. R is the percentage. R must be written as a decimal. Write it on the side here. 1 plus or minus R equals B. We saw on the last page that we didn't just write 1% or 3.2%. We wrote 100 plus 1% or 100 minus 3.2%. We took 100%, which is 1, and added or subtracted our percent from it. And so that's what we're going to do whenever we have a percent. X is still the time unit, and Y is the final amount. Box it at the bottom. 1 plus R, box the whole thing. 1 plus R represents the change to the original amount, since 100% equals 1 when written as a decimal. And that change can either be an increase or a decrease. So you can add or subtract to 100 or to 1. Let's go to the next page. Set up an exponential equation for the following scenarios. You may use variable names as you see fit. So some of them provide variable names. Number five, you see sorry, I don't know what I was reading. Number five, a gold bar initially valued at $5,000 increases by 2% each week. Opposite, valued at $500. That's our sorry, initially valued at $5,000. I don't know, you're saying 500. A is 5,000. That's our starting value. It increases by 2% each week. Underline that. Increases, put an arrow. If this is y equals a times b to the power of x, we know that a is 5,000. B is not 2%. It's 2% more than 5,000, then 2% more than that, then 2% more than that, then 2% more than that, and so on. It's going to be increasing by whatever the original amount is, 100% plus 2%. That's 102%. Divide it by 100, turn it into a decimal, and you get 1.02. Y equals 5,000 times 1.02 to the power of W. We're actually using W instead of X for time. A newly pumped tire measured at 35 psi, box that, deflates at a rate of 0.0005% each day. Deflates at a rate of block percent. Underline that. We know that A is 35 and B is 100% minus 0.0005%. It's going to take me 1 second. 1 minus 0. Don't forget all your zeros. There should be 3 zeros after the decimal, meaning you have 3 nines when you subtract. 0.9995 divided by 100. Sorry, that's 0.009995. So y equals your initial value, 35, times your b value, 0.009995 to the power of d. Oh, I'm sorry. That was wrong. I was looking at it like this is wrong. When you subtract 0.0005 from 100, you get 99.999%. 99.9995% divided by 100.9999995. 5 nines. Y equals 35 times 0.99999 to the power of d. Finally, Karen opens a savings account and deposits $2,000 into the account. Her bank offers her a 4% annual interest for T years. Underline that. Here, if y equals a times b to the power of x, we're using this formula because it's a percent, or it's increasing, so we can use an exponential formula. The initial value is $2,000, and her b value is, what is it increasing by every year? 4%. So 100% plus 4% is 104%. 104 divided by 100 is 1.04. Y equals 2,000 times 1.04 to the power of t. Okay. Now, one last thing, you don't have to find b in this order, right? In the earlier examples, we did it in a slightly different way. You can take 4%. Let's write it on the side. You can take your 4% and convert it to a decimal to start, 0.04, and then do 1 minus 0.04. I'm sorry, plus, because it's increasing. So you could do it and get 1.04. Okay? You don't have to do 100 plus 4%. You can just convert it first. You have to use 100% if you're using it in percent form. You have to use 1 here in blue if you're using it in decimal form. Okay? But either way, your decimal will be slightly bigger or slightly below 1. Your b value here, your final b value should be bigger or smaller than 1. And that's what we saw with increase, growth, and decay from last week. Next page. So try these problems. There's 6 of them. Pause the video. I'm gonna reset for a second. But when we come back, I'm gonna go over these 6. Unfortunately, I can't call anyone. So you'll just have to go through the video with me and check your answers. Then we're gonna go through the second part of the lesson, and then you'll do that independent practice, and then I'll go over it. All right? This is my first warning that I do need the exit ticket from you tomorrow. Okay, so try that independent practice. Give me 1 sec. Alrighty. So hopefully you had time to do the independent practice and pause the video. Let's go through each question. Question 1, based on the exponential equations shown, what is the rate of growth or decay of each one? Simplify each expression, if necessary, before dividing. Then write growth or decay as your final answer. So if we're looking for the rate of growth or decay, look at your reference sheet. Rate of growth is the letter R, not B. B includes the original 100%. Whatever happened to it. Was it increased or decreased? So we can tell that by looking at the B value here. But to find the rate, we're going to need to do some work on the B value. For the first one, the B value is 1.32. that 7 is the initial value. We're not focused on that. 1.32 is greater than 1, so we know that it was growth. The original amount grew from 100% to whatever 1.32 is as a percent. How much did it grow by? Well, if we take away the original 100%, the 1, we're going to be left with 0.32. We multiply that by 100, we see that it's a 32% increase. Next, 0.67 is less than 1, so it decayed. The original percent went down. How much did it go down by? Well, it started with 1, it went down to 0.67. What's the difference? 0.33. Multiply it by 100, and we see it was a 33% decrease. The last two were a little trickier because if you look closely at the exponent, it's not to the power of x, and it needs to be simplified. So the first thing to do is y equals 9.1.032 to the power of 2 and another parentheses to the power of x. When you have 2x, that's 2 times x, that's power to a power. Box your inner exponent expression. You need to type that into Desmos to see what 1.032 to the power of 2 is. Okay, so that's y equals 9, 1.065024 to the power of x. It's bigger than 1, so it was growth, not decay. Well, there I am. Huge. Great. Slide that over. So it's growth. How much did it grow by? Well, we do 1 minus 1.065024. We get 0.065024. And we multiply it by 100, and we see that it's a 6.5024% increase. Writing decimals out like this may not always be required. The question will tell you how many decimals to round to. Here, because we need to simplify the next one as well, we won't write all the decimals. So for the next one, we type in 1.34 to the power of -3 to simplify. It becomes 10, parentheses 0.41561, we can say, to the power of x. It's less than 1, so it's decaying. 1 minus 0.41561 gives us about 0.5844. So we can say it's a 58.44% decrease when we multiply it by 100. Okay. Number 2, write an equation to model the table of x and y values given below. Well, we already see the initial value here, a comma 0, or 0 comma a, sorry, it's the y-intercept. So a is 8. To figure out the common value, the b value, we know that the b value is what we multiply by each step. So let's do the opposite with these output values. Let's divide them backwards to figure out what's being multiplied. What is 343 over 64, in parentheses, type it on Desmos, divided by 49 over 8, in parentheses? It's 7 over 8. What is 49 over 8 divided by 7? 7 over 8. So make sure you put it in parentheses. And what is 7 divided by 8? It's 7 over 8 as a fraction. So 7 over 8 is our common factor. It's what we multiply by every step. 8 times 7/8 is 7. 7 times 7/8 is 49 over 8. 49 over 8 times 7/8. So y equals a times b to the x. Y equals 8 times 7 over 8 to the power of x. Okay. Number 3, sketch the graph of the function. For number 3, type that into Desmos. The only thing is that when you're trying to type -2 in the exponent, it's going to force it down. You have to use parentheses when you type it into Desmos. Let me show you that. Type it in as y equals 2 to the power of parentheses x minus 2. Parentheses. Then go down. -1. Okay. You get some points. Press the gear and make a table. You get even more points. So let's graph our points. So we have -2, -0.9375, -1, -0.875, 0, -0.75, 1, -0.5, 2, 0, and we can extend the table. 3, 1, 4, 3, and even 5, 7. Okay, so we should be good to go. So we see here, we're never going to touch -1. We shifted down 1 from the x-axis. 0, -0.75, -1, -0.5, getting closer and closer to -1, 2, 0, so on the x-axis, 1, 2, 3, 1, over 3, up 1, 4, 3, and we said 5, 7, the top. Start from the flatter side and then work your way up. Don't forget to label. 2 to the power of x minus 2 minus 1. Okay. Number 4. True or false? Exponential decay means that the base of an exponent is a negative number. And that is false. Exponential decay means the base is a decimal or fraction between 0 and 1. When we decreased or when we taxed that person's salary at 4.7%, the decimal didn't become, the base didn't become negative. It just became a decimal smaller than 1. It became 0.968. They were making 96% of their pay every year because they had to pay 4% to tax. In this example, none of choice 2, this one wasn't a negative b value. It was just a decimal less than 1, meaning we decreased by 33% every year, and this person's making 67% every year of 6. Number 5, they're actually all true statements. In the parent function or the basic function, you'll never touch the negative part of the y value. The function y equals b to the power of x has all positive numbers in its range. range our outputs. The parent function, if we draw a t and graph it, it will always get closer and closer to touching the x-axis. Increasing exponential functions increase at a greater rate than increasing linear functions. Yes, exponential always increases faster than linear. That's what exponential means. And number 3, in an exponential function, the base is constant. Yes, the b value stays the same, and the power, or the exponent, is the variable. Number 4, the domain of an exponential function is all real numbers. Domain are x values. And yes, again, the graph will go all the way left and go all the way up and to the right. If it's increasing, it'll go all the way left and up and all the way to the right if it's decreasing. It'll increase left and right always. Finally, number 6, which of the following shows an exponential growth at a rate of 100%? Underline that, rate of 100%. R is 100%. Remember, these values here are all B. B is found as 1 plus or minus R. So if the original amount is 100% and we're growing by 100%, we need to add another 100%. Next year, we'll have 200% of our original amount. 200% written as a decimal, I say in quotes, is 2. Choice B. Every year we multiply by 2. If we have a growth rate of 100%, we're doubling the amount, the original amount every year. We start with 100%, we increase by 100%. Okay. Let's go through the next part of the lesson. Compounding interest, page 8. So for page 8, the last part of this exponential journey is compounding interest. Banking overview. Banks operate by having customers invest and save their money with the bank, right? That's how a bank makes money. They have people save their money with them over long periods of time. But because there's so many banks, these banks often have to compete with one another by offering their customers competitive interest rates. Interest is the amount of money that people earn just by leaving their money with a certain bank. So the bank will offer them more money over X amount of years if they save their money over longer periods of time. Some banks will offer compounding interest. Let's read it together. When a deposit is kept for T number of years, the interest can get compounded N times or X amount of times each year, such as quarterly, monthly, semi-annually, within those years. Banks offer this so that the interest applies more often within the year and becomes more competitive. So they'll say you have a 5% interest rate every year, but it's being compounded twice a year or semi-annually. So you're earning technically a little more than what 5% would give you in 1 year. Okay, so let's take a look at some ways they can compound it. Compounding annually or just annually. Oh, sorry, let me open Zoom. Share my screen again. Annually means one time each year. Semi-annually means 2 times each year. Quarterly, like there are 4 quarters in a dollar, or 4 quarters in a year. Monthly means 12 times a year. Weekly, 52 times a year. And daily, 365 times a year. Probably won't see a bank doing that. The equation we used, y equals a parentheses 1 plus or minus r to the power of x, becomes a bit more complex, and it is one you should be prepared to write on the reference sheet on the day of the exam, in case it comes up. Let's underline the equation we've used and just write down the equation again. A, 1 plus or minus R to the power of X. The compounding interest formula is a little different. It uses slightly different variables. Instead of Y equals, it's A equals for total amount, capital A. And instead of lowercase a for the initial amount, it's P for the principal, which is another way of saying starting amount when you're at a bank. Instead of doing 1 plus or minus R, you do 1 plus or minus R divided by N. You're going to take the interest rate, 5% every year, and divide that percent by however many times it's going to be compounded or hit within the year. So they're not going to give you 5% twice in the year. They're going to give you 2.5 and then another 2.5. If you have a 10% interest rate every year, they'll give you 5% each time if you're getting compounded semi-annually. If you have quarterly, they'll do 10% divided by 4. It all depends on what they offer you. So you have to read each question carefully. This thing stopped sharing so quickly. Bear with me, sorry. Another thing you have to do is multiply the variable T, your time, how long you're going to leave it in the bank. You have to multiply that by however many times it's getting compounded. Okay. So in your exponent, you have n times t or n times x. All right. Let's try it in the quick practice. Yusuf deposits $50 into a savings account that pays 3.25% annual interest compounded quarterly. What will his investment be worth in 12 years if he makes no other deposits or withdrawals? So, box every piece of information given to us. He deposits $50. That's our A value, his starting amount. The savings account is going to pay 3.25% annual interest. Let's box that. That's our R value. That's our percentage. R is the percent, 3.25%. But they're not going to pay this annual interest. Annual means every year. They're not going to pay this just once a year. They're compounding it quarterly. Underline that. Compounding quarterly means that n equals 4. They're going to hit it, they're going to cut it. Sorry, they're going to apply it 4 times. What will his investment be worth in 12 years if he chooses to go with this savings account and he doesn't touch it for 12 years? Our x value or our time is 12, or t is 12. So let's plug it into the formula. There's 2 ways to do this. We can plug it into the formula we used earlier. Y equals A times B to the power of X. A is $50. B is going to be 1 plus R over N. Okay. And what that means, it's going to be 1 plus 3.25%. We have to write that as a decimal, so 0.0325. It's divided by 100. Divided by n, where n equals 4. Type that all into decimals. Only the decimal is getting divided by 4. 1 is not. That 3.25% is divided by 4 because it's applied 4 times in 1 year to make up the full 3.25%. B is going to equal 1.008125. For X, it's 12 years, but in just 1 year, he gets four interest applications, right? It gets compounded 4 times in 1 year. So over 12 years, it's 12 times 4. This B value gets applied 48 times. Again, it's not 3.25% 12 times. That would be 1.0325 to the power of 12. Here, it's 3.25 divided by 4, and then that is added to 100% or added to 1. That new B value is raised to the power of 48 because that's going to happen 48 times. It's smaller than 3.25, but it's applied more times than what it would be if it wasn't compounded. And it's a little bit difficult to fully understand, but we take the interest rate they give, we divide it by the amount of times that it's going to be applied or compounded, and we raise our exponent or our years, we multiply our years by that same amount that it's getting compounded. When we put the B value, the A value, and the X value into our equation, we have Y equals 50 times 1.008125 to the power of 48, which rounds to about 73.73. Choice B. If we wanted to use the equation from above, you prefer to just memorize that one. Y equals A equals P, parentheses 1 plus R over N to the power of NT. That's the one on your reference sheet. The principal is the original amount, $50, 1 plus the rate, 0.0325. Sorry, I wrote it a little too big. Divided by 4 to the power of 4 times 12. Type that all into decimals and you'll get the same answer, 73.73. Okay. Take a moment and let's continue with the independent practice, questions 1 through 11, and then you'll do the exit ticket. I'll go through the answers to questions 1 through 11 in just a moment. Okay, let's go through the second round of independent practice. The first question involved substitution. Here we're given an expression that has an exponent, but we haven't really seen this since day 1, where we were evaluating functions. They want me to figure out the population P in the year 2025. Here, it's important to know T represents the number of years after 1900. So T is not 2025. T is 2025 minus 1900, or 125 years since 1900. Using the equation, estimate the population. So wherever we see T, we're going to draw parentheses around T, not the exponents, not the coefficients, just T. Rewrite the equation, 0.0089, parentheses, 1.25 to the power of 2, plus 1.1149 to the times 125, plus 78.4491. We go left to right on Desmos, that entire expression. And we get 356.8741. It's always D, 356.9. Take the 8, round it up based on the answer choices. Number 2, using the function or based on the equation, how much more money was earned in revenue for week 3 than for week 5? Another one where we have to substitute. Because the equation models the revenue earned, Y. Y is the amount of money earned, the total, over each week X. X is the time period. So when you're using these exponential functions, the exponent represents time. X is time. So in the third week, I think the fastest way to do this is to type it into Desmos. Into Desmos. Type the equation in. We know it's decaying. That B value is 0.61. So only 61% was earned from the previous week. And then make a table with Desmos. Find the third value and the fifth value of X. We see 3. The Y value is 27.16, 2816. The fifth value, 10.10724. When you subtract 27.162816 minus 10.10724, how much more money? Well, 17.055532. 17.06 millions more. Number 3. The Franklins inherited $3,500, which they wanted to invest for their child's future college expenses. If they invested at 8.25% with annual interest compounded monthly, determine the value of the account in dollars after 5 years. So let's use our formula. Y equals A parentheses 1 plus R over N to the power of X times N, or N times T. It could be X, it could be T, whichever variable you feel more comfortable with for time in the exponent. We know that A is $3,500. R is 8.25%. Divided by 100 is 0.0825. Divided and sorry, and N is compounded monthly, so N is 12. X is going to be 5 years. So let's plug it all in. We start with $3,500 getting multiplied by the original amount 1 or 100% plus 0.0825 over 12. We're taking our 8.25, we're dividing it, and we're giving them that percent. We're giving them whatever it is divided by 12. We're giving them that new percent every month. We're not giving them 8.25% in just one shot. We're dividing it amongst all 12 months in the year. They're going to do this for 5 years, but it's going to happen 12 times every year. So 5 times 12 in the exponent. We type that in to Desmos, left to right. Again, don't forget to put parentheses in your exponent, since there's 2 things in there. 5,279.61. Okay, next page. Number 4. Joe deposits $4,000 into a certificate of deposit CD at his local bank. The CD earns 3% interest compounded annually. The value of the CD in x years can be found using the function blah. Whenever we have a percentage like this, it's going to be an exponential function. So 1 and 2 are out because they are linear. These are linear functions. We don't want those. Between number 3 and 4, they both have the same 4,000, and that's correct because that's our initial value. That's how much he deposits. A is 4,000. It's earning 3% interest, so B is 100 plus 3, or 100% plus 3%, 103%. 103% divided by 100 is 1.03, not 1.3. If someone picks number 3, that represents a 30% increase. 0.3 changed back into a percent multiplied by 100 is 30% instead of 3%. So 3% is 0.03. Number 5, I think the fastest way to do number 5 is to convert the graph into a table. X is our years. Y is the population in thousands. So 1980, 1990, 2000, 2010, 2020. In 1980, we have 2,000. 1990, 4,000. 2000, 8,000. 2010, 16,000. How much will it be in 2020? Well, going up exponentially by 2, doubling. So the next amount should be 32,000. Choice B. If we graphed it, that'll be right there. Follows that beautiful exponential pattern that's going on. Okay. Choice 6, Kathy deposits $25 into an investment account with an annual interest rate of 5%. If she makes no other deposits or withdrawals, how much money will be in her account at the end of 15 years? Here, there's no compounding. So she deposits $25 and they're giving her 5% every year. She's not getting any special kind of competitive interest rate. A is $25, and the 5% is going to be a part of our B. But remember, your percent is the letter R, the rate. R is 5%. If we divide it by 100, that's 0.05. This is her investment account. So she's earning 5% more every year. It's 100 plus 5%, 105%, or 1 plus 0.05. So B is 1 plus 0.05. A little differently than how we did it earlier, but either way, as long as you get 1.05, you're showing that she went up by 5% every year. At the end of 15 years, so X, put a little X next to it, X is 15. Y equals A, 25, times B to the power of X. Plug it into Desmos and you get $51.97 in 15 years. Okay. Question 7. Now we're going into a little more review questions. Which one represents exponential decay? Just like number 1 from the first independent practice, none of these are fully simplified until we have x as our only exponent. So these all need to be rewritten. This negative x needs to be written as negative 1x, or negative 1 times x. Negative 1 with 1/4. X outside. 1.8 to the negative x, 1.8 to the negative 1 to the x, 2.3 to the power of 2, then to the power of x, and 4 to the power of 1/2 to the power of x. Simplify each of those inner expressions on Desmos. Then raise them to the power of x and see which one is decay. 1/4 to the negative 1 is just 4. 1.8 to the negative 1 becomes 0.555 repeating, 0.5 with a bar on top to the power of x. Number 3, 2.3 squared becomes 5.29 to the power of x. 4 to the 1/2 becomes 2 to the power of x. And so this one is the only one that's decaying. For decay, b is less than 1. B is between 0 and 1. It's a decimal, right? Because if your percent is decreasing, you take your 100% and you subtract from it. So your decimal is going to be less than 1 or less than 100%. Number 8, which situation represents exponential growth? Aiden adds $10 to a jar each week. If you're adding, you're doing plus 10, that's linear. Number 2, pine tree grows 1.5 feet per year. Feet per year represents slope, but also growth, growing, that's linear. Growing 1.5 feet. Number 3, Ella earns $20 per hour babysitting. That's a constant rate of change. That's linear. Number 4 must be our answer, but why? The number of people majoring in computer science doubles every 5 years, times 2. Every 5 years, we multiply. That's exponential. Number 9, the 11th term of the sequence is... So the long way to do it is just to write out 1, 2, 3, 4, 7 more slots. And you just keep multiplying by -2. That's the pattern here. Multiplication, and it's by a negative number. But we should remember that multiplying in a sequence is geometric. And we're given this formula on the day of the test. If we want the 11th term, that's A11, where n is 11. A1 is 3 here, that's the first term. The R value here is the common ratio. It's being multiplied by -2. And it's raised to the power of 11 minus 1 to represent how many times are we going to multiply by -2. We should be multiplying by -2 10 times. That's our exponent. Type this into Desmos. A11 is 3072. Positive. Right? Every odd term in the sequence is positive. The first one is positive and the third one is positive. So the 11th one should also be positive. Number 10, a good review of the unit conversions, dimensional analysis that we did. We want to figure out the correct way to figure out the cost in dollars per gallon. So number 4 doesn't work because they both have euros on the top. Euros don't cancel. Number 3 doesn't work. Euros on the top, and again, euros on the top. Those won't cancel. We need euros on the top and the bottom. Number 2, euros cancels, but liters, one is on the bottom and the other is on the bottom. We need one on the top and one on the bottom. Doesn't work. Number 1, euros cancels, one on top, one on bottom. Liters cancels, so we're left with dollars per gallon. Dollars per gallon, or dollars over gallon. Number 1 is correct. Number 10, I love this question. Here's a piecewise function what is the value of f of 3? When you have a piecewise function, remember there's more than one piece that defines this function, and they have restrictions on them based on the x value. Here, the first piece, if you want to circle it, is used when x is less than 3. The second piece, you can circle it also, is used when x is greater than or equal to 3. And I realize my signs are wrong. The first one is when x is greater than 3. And the second one is when x is less than or equal to 3. It didn't really matter though, right? Because here they're asking for f of 3. If this is always f of x here is 3. When x is 3, that means x equals 3. We have to use the second piece, the piece where x equals 3. The first piece does not equal 3. Only the second piece will give you the correct output of 3. You have to use the second piece. F of 3 equals negative parentheses squared plus 15. Remember, when you're changing your variable into a number, you have to use parentheses. Leave the negative sign outside, leave the squared on top. This is negative 3 squared plus 15. Type that into Desmos with your parentheses, and you're going to get 6. Negative parentheses 3 inside, exponent 2 outside, plus 15. Okay? By setting these up correctly, you should get full credit on those types of problems. I want to see that happen. Complete the exit ticket for this lesson, and then watch the video for the other lesson to check your work for that one too. Thank you for your time here. If you need to go back and pause anything, you absolutely can, and rewatch this anytime you need. I know this lesson was a little tricky, so make sure you rewatch it as necessary. And finish your notes, finish the exit ticket and the homework. Thank you. See you tomorrow.